integrations? Nothing is yes. So if we do here, the integration is log I minus E by R. And this side we have R by L T. R by L into T. Limit, we can take it. In the beginning, how much is the current, beta? In the beginning, we have assumed there is no current. So at any time T, my current, let's say the I. So give me a log I minus E by R divided by minus E by R. This side you have minus R by L T. The log is easy to remove here as exponentials. So you can remove here the log. If you remove the log, it is exponentials. Okay, so current comes out to be slightly here E by R 1 minus exponential factors. Now this result is also looks similar to RC circuit. Derivation is also similar to the RC circuit, and the results are also similar to the RC circuit. Eddy current, regarding the eddy current, I want to tell you that eddy current is not a topic. It's just a simple one line topic is this. Okay, there is no formula for the eddy current in our syllabus. No problems are there on the eddy current syllabus. The eddy current is not at all a topic. It's just a one simple 2-line topic is this. I will tell you. You can read from the book also. I will tell you also. Yes, Sunath.
Sir, growth circuit means I is positive or di by dt is positive.
Growth circuit means current is increasing. So when current is increasing, my di by dt is increasing.
Okay, sir.
Okay, current increasing, di by dt should be positive. Induced electric field, it is not in the NCERT, right? It is not in the NCERT. Mutual inductance there in this case? No. In this problems, see here, inductor is a self-inductance. Only single circuit is there. We don't have any second circuit here. So it is a single circuit. And in that single circuit, you have internal resistance, circuit resistance there, and inductance is also my circuit inductance.
Hello,
Yes,
sir.
Satish. Hello.
Sir, what do you mean by LR, sir? L means
LR circuit means circuit is a combination of different types of elements. Okay, we have discussed about the resistance, we have discussed about the capacitor, we discussed about the batteries. What is common in all that?
combination
The
of
drop
inductance
potential.
and resistance, sir.
Your voice is not coming, Satish.
Sir, the combination of resistance and inductance is LR, sir.
Yes. LR circuit means we are going to have a combination of inductor and resistor.
Okay, sir.
Battery is also included here. It is not without battery, it is with the battery.
Okay, sir. Thank you, sir.
Yes, Shiva.
So generally across the inductor, the potential is taken as minus L into di by dt, no, sir?
Yes, minus L into di by dt, yes.
So there, what is the minus indicates?
Minus sign come from the Lenz's law. flux, it opposes the flux change. Okay. So in my circuit here, so in the circuit, what is the minus sign you can indicate here is, you can take the help of the minus sign to get here the relation between the potential polarity and the di by dt polarity. If di by dt is increasing, then potential is negative. Okay, potential is negative. What is the meaning of potential negative here? Is potential drop. Potential drop is negative in the direction of current. Suppose inductor is there, current is going to be there, and di by dt is a positive, then potential drop. di by dt positive, then v is negative. So v comes out to be negative. In the direction of current, your potential is going to be dropped. If my current is decreasing, if the current is going to be decreasing, decrease of current means potential is going to be increased in the direction of current. Polarity is opposite to the current.
It is just for giving the directions.
Yes, it is just to give here the directions.
Okay, sir.
Conceptual meaning of the negative sign we have discussed in the Faraday's law. Faraday's law says that EMF always opposes its reason. Again, Lenz's law says that negative sign indicate that flux change opposes its cause. Okay.
Yes.
But in the circuit, it also has a polarity meaning also. So you can take this negative sign with polarity. So this is my first LR circuit. The easiest LR circuit is this. In this easier LR circuit, you have one inductor, one resistance, one battery. It's called growth circuit, meaning it is the simplest growth circuit. There can be a many complicated growth circuit is also possible. It's the simplest growth circuit. What is a growth here means? Whose growth is that? It's a current growth. Just like in my charging circuit, RC charging circuit, the charge rise. Here, my current is going to be rise. If I connect the battery, so the battery is going to be increase the current. Okay, battery try to increase here the current. Without inductor, if I just connect the battery to the resistance, then what happens? If I just connect the battery to the resistance directly, so I know that current will be I by R. So initially current was 0, then it will go to E by R directly. But my inductor has a property to oppose the current change. If the battery try to increase the current, my inductor opposes it. Resistance don't oppose the current change. If we have only resistance and only battery, your current can go from 0 to E by R suddenly. But through the inductor, this is not going to be happens. Because what is the basic nature of the inductor? The basic nature of the inductor is to oppose the current change. The battery try to increase the current, inductor is going to be opposed. Okay. As a result, inductor drop the potentials. Okay. Inductor here drop the potentials because di by dt is a positive. When current rise, potential fall. Okay. So polarity is falling polarity. Potential fall in the direction of current. For resistance, we have normal polarity here, plus minus in the direction of current. So inductor oppose. How oppose? It will satisfy the Kirchhoff law. Okay. Inductor oppose, battery push, inductor oppose, right? But they both are going to be satisfy the Kirchhoff law. If you write here the Kirchhoff law, what is the Kirchhoff law says? As I'm going to be crossing to the battery, it will rise E. Then I crossing the inductor, it will drop the potential. I'm crossing the resistance, it will drop the potentials. That's my differential equation of current and time. E, R, L, they are constants. So we have simple differential equation of current and time. So if we separate the current and separate the time, we're getting here exponential equations. Okay? This integration is simple log integrations. It's a dx by x type of integration. Log integration is there. So what I'm getting is a current is exponential. Exponentially, it is going to be changing. So many times I told you, nature like exponential functions. Everything happen in the natures, it follow the exponential variations. So current in the inductor is also going to be rise exponentially. Okay. If we understand these equations, we can understand the general behavior of the inductors. So in my this expressions, if you try to consider that time equal to 0, my exponential factor is 0. So its value is 1. Exponential value is 1 at time equal to 0. So how much is my current coming? Current coming out to be 0 at time 0. So as my time tends to infinity, this exponential factor goes toward the 0. Because power goes toward infinity, exponential factor goes toward the 0. And current is approached toward the value E by R. So if we try to plot here the graph, so in a graph, you can see that it's rising, rising, rising. It is approaching toward my constant value. After a very long time, how much is the current here? E by R. Right? So it is going to be here my current. So current is growing. Exponentially, it is growing. And will approach toward a stage, a constant state. That is called steady state. It is approached toward a steady state. And this is almost similar to your capacitor behaviors. Okay, quite similarities there. And this exponential, regarding the exponential, I told you, this exponential is a function who change constant percentage every fixed interval of time. Every fixed interval of time, it is going to change your constant potentials. And this fixed time interval, we call time constants. So in this case, how my exponential is changing? This exponential factor, this exponential factor is your minus RT by L. So I can just say it's a time constant. Here is L by R. So it is going to be have a time constant L by R. What is the meaning of L by R? It's meaning thereby, after every one time constants, this exponential factor fall by E factors. If timing is equal to tau, okay. If timing is equal to tau, my current will be 1 minus 1 by E. If timing is equal to 2 tau, your current will be E by R, 1 minus 1 by E squares. And this I2, it is still equals to your, try to calculate here. This factor of 1 by E in the RC circuit, I told you, same thing is here. 1 by E means 37, and this is going to be a 67 nearly. If you calculate in percentage, something around 67% rise, which is also going to represent here 67% rise. In a first tau, it will rise 67%, and between tau and 2 tau, again, it is going to rise here 67%. Okay, 67% current is going to be rise. So whatever the remaining thing is left here, it is going to 67% rise. Okay, it will maintain here constant percentage. That is the nature of the exponential factors. Current after passing inductor, it alter. Yes, it is altering. Na? Current is changing, exponentially changing. Na? The way current through the inductor is changing. Who is changing? The responsible is a battery. Inductor does not allow the current to change, but battery want to change. Inductor only going to oppose it. Remember one thing here. Inductor is not changing. Who is changing the current? Battery. Battery try to change the current. And inductor has to oppose that change. Okay. Without inductor, your current can be easily reached to the E by R in no time. The battery will give the current E by R easily, but inductor is opposing. That's why it is rising slowly. It takes a time to rise. So I hope you understand here. Inductor is opposing. Yes, Sunat.
Sir, at t equal to infinity, as it is I equal to E by R, then there will be no effect of inductor at t infinity, sir. Long time.
Yes. I'm coming to that
Sir,
point here.
why that is?
Can discuss here this point here. So first of all, I hope you understand here the meaning of these equations. I'm coming to this point. At time equal to 0, this exponential factor here is 1, so current is 0. As time tends to infinity, your exponential factor goes to 0. Current is approaching toward a constant value. Okay? And when you're rising exponentially, so just like RC circuit, we can define here tau. The tau value is a L by R. Okay? A few more points you can notice here, then we can generalize its results. First one is the potential drop across the resistance. Potential drop across the resistance is IR. I value is a, so this RR is going to be cancelled out, and you can see here through the resistance how your potential is changing. So through the resistance, I can say potential is rising exponentially. So in the beginning, there is no potential across the resistance, and slowly the whole of the battery will be dropped across the resistance, right? Through the inductor, it is L di by dt. Current is E by R 1 minus exponential factors. If you differentiate, exponential factor is going to be exponential into its derivatives, right? And this derivative is my tau. When you differentiate it exponential, it will give exponential into its chain rule minus 1 by tau. Tau value is L by R. Okay, so give me here L by R. So this tau is cancelling here as L by R. So potential across the inductors is falling exponentially. This exponential factor is a 1 in the beginning, and then it just goes to 0 at the end. So if we plot the potentials across the inductors, so it is having a reverse behavior to my resistance. It is falling exponentially toward the 0. So if we club together all these properties, I'm getting here some general feature of the LR circuit. Once again, just listen here. So what is happening here is, if you notice, current is rising, okay, and it is approaching toward a constant value E by R. If I think about the potential across the resistor, it is also rising and approaching toward a constant value E. If I think about the inductor potential, it is falling at 0. So in the beginning it was E, at the end it is R. So based on this feature, I'm getting here some characteristics of the LR circuit. And this characteristics is also followed by a complex circuit also. So meaning thereby, in the beginning of my LR circuit here, when you just about to be touch it here, it will always approach toward a steady state. After a long time, it will approach toward a steady state. Whatever is the beginning one, it is approached toward a steady state. And steady state, just like RC circuit, is going to be a kind of equilibrium situations. It is equilibrium situations where everything approach toward constants. All parameters approach to a constant value. Approach to a constant value. Okay. So first and most important thing about the LR circuit is that it will always try to approach steady state. Try to reach steady state. And how it will try to reach? It is try to reach exponentially. It is try to reach steady state exponentially. Now, exponential is the general behaviors. Okay, we have taken one simple circuit, but in a complex circuit also it is exponentials. It is always going to be approached exponentially, right? So the moment here we have discussed in this case. So in the exponential situations, what happened? The whole of the battery is going to be drop across the resistor, and there is a zero drop is there across the inductor. So when there is zero drop across the inductors, okay? So zero drop means it is not opposing. It is not opposing the current change. Why it is not opposing the current change? Because current has reached a constant value. So in a steady state, it does not oppose the current change, and current is going to be here constant. So in a steady state, my inductor is simply behave as a plain wires. Okay? It does not oppose anything. Because ultimately, whole of the battery is now drop across the resistance, and it is going to be reach here my constant. That is my maximum possible current in the circuit. So at steady state, current reach its maximum growth. So di by dt is 0. When I reach to the maximum growth, di by dt is 0. So I can say that inductor drops 0 potentials. So this inductor is going to be drop no potential like a plain wires. So you can think of inductor as a plain wires. Inductor behave as a plain wires. Because my plain wire does not drop any potential, na? So inductor also behave as a plain wires. Okay. And when I just behave as a plain wires, it is going to behave as a plain wires when current is maximum steady state. It's going to have full growth. Okay. It's going to be have a full growth. So in the beginning, how it is behaving? Initially, when you're going to be switch is about to be closed. So just before the switch closed, current was 0. And inductor don't suddenly change the current. Okay, it will slowly increase the current. So an inductor is going to be whenever you try to change the current, inductor does not allow sudden change in the current. Right? So in the beginning, it blocks the current. Simply, it will block the current. When it is simply block here the current, so whole of the battery is going to be drop across the inductor only. And there is a 0 potential drop across the resistance. So one important feature I can consider here is inductor does not allow jump in the current. Okay, it does not allow jump in the currents. So initially it blocked the current. It simply block here the current. So meaning thereby initially if you have a circuit, so for initial circuit your inductor is just going to be like a blockage. It does not allow the current to be passed. It does not allow the current to be passed in the beginning. Right? I hope you understand the point here. It simply behave as a block. The inductor block. The inductor is going to block the current. I hope you understand the point here. Almost similar to the RC circuit, right?
Then in the graph of potential in inductors, why you didn't take minus sign?
Why?
You didn't take minus sign.
Why we
equal
have
to
not
minus L.
taken minus sign?
In this.
So minus minus, it's going to be here. This side minus minus getting a plus. At here, this point. This side you're saying here minus LDI by
Yes,
dt.
sir.
You can take the minus sign also. Yeah, this minus sign give me the polarity. Here we are just in the magnitude, so
Okay, sir.
magnitude only I have just written over here. So in the
Okay.
potential across the resistance also minus IR. It is always minus IR.
Okay, sir.
Okay. For polarity purpose, you can use here the minus sign, or anywhere else. We're just talking about the magnitude.
Okay, sir.
When you apply the Kirchhoff law, then you need to be clear about the sign. Other than the Kirchhoff law, you just talk about the magnitudes of any elements. Potential across the capacitor is Q by C. We don't talk about the plus minus sign. Potential across the resistance, it is IR. We don't talk about the plus minus sign. Okay? But when we write the Kirchhoff law, in a Kirchhoff law, sign is important. So in Kirchhoff law writing, you take care about the sign. In general, magnitude is important. Okay. So I hope you understand the point here. The first one, it is always try to reach the steady state. So how I know it's a steady state? Simply means current maximum, that is a steady state. When current is maximum, potential across the inductor will be zero. It's a sure sign of steady state. And when you have a potential zero across the inductor, it will simply behave like a plane wires. You can take it as a plane wires. Initially, in the beginning, if I am going to consider, the inductor does not allow sudden change in the current. So it does not allow the current to jump. So it does not allow the current to jump. So initially current is zero, so it is going to be zero. If current is zero, it is zero. It takes a time for the current to change, right? So current in the beginning, if it is zero, it is going to be remain zero after the switch close. So before the switch close, if current is zero, so after the switch close, it is going to be zero. But it will not remain zero forever. It is not zero forever. Just after the switch close, your current is going to be zero. In RC circuit, if you remember, in the previous, all the circuit we have discussed, we suddenly change the current. But inductor don't allow the current to be changed suddenly. Now, fourth important property we can consider here is, what is the time constant? Time constant, we can say it's a L by R. Here R is going to be equivalent resistance for complicated circuit. So R is the resistance experienced by inductor. Resistance field by inductors. Okay. So in the more complex circuit, your time constant will be L by R. Right? I hope you understand the point, yes? So it's almost similar to our RC circuit. Again, quite similar to the RC circuit. Let's take here one example. I can take it here to become a little clear. Let's say we have inductor. This has a resistance. And this one has a resistance. Sorry, resistance. And we have a battery. So we have three resistance, one battery, and one inductors. So starting one, you can consider battery is not there. Okay, battery is not connected. And at time equal to 0, switch is closed. If we close the switch at time equal to 0, the question here is find the current just after the switch close. Find the current at time after long time, infinity, time after long time. Then you can find out the current at general time here t. What is the value of current at general time here t? This question is almost look like your RC circuit, and you have to solve like a RC circuit only. Okay, just solve like a RC circuit. So LR circuit and RC circuits are almost going to be a similar one. So just to understand here this approach, we can discuss here one problem. So again, so how to approach here is first condition is that time 0. So at time 0, what is the current initially before the switching? Whatever the current we have before the switching, my same current is going to remain after the switching also. Right? So it is a 0 before. Okay. So here is a 0 before. So I don't have any current before the switch. I don't have any current before the switch. Now I told you that after the switching, current is going to be 0, but be careful. The statements are very misleading. So if I just close, then why current is going to be 0? Current is going to be 0 because inductor don't like a jump in the current. That's it. Again, inductor don't like a jump in the currents. So conductor don't like a jump in the current. So in the inductor branch, your current is not going to be jumping. But in this other branches, there is no inductors. So if you just notice here the lower branch, then in my lower branch, there is no inductors. So in the lower branch, current can jump. But in my upper branch, where there is an inductor, current is not going to be jump. Right? So current inductor block. Inductor is going to be block the current jump. It doesn't allow the current to be jumped. So initially, my current is 0. So through the inductors, your just suddenly current can change. It will take a time. So here I'm just saying about the sudden current. No? So just at time equal to 0, my current is 0. And time 0 plus, I'm saying just the moment you close the switch, inductor does not allow any current. It will be 0 in the branch. But this type of problem is not there in the resistance. Resistances don't have this type of property. Resistance can change the current very easily. So battery is there, current will be there. So through my lower branch, there is no inductor, and I can say current can flow in the lower branch very easily. So what is the current flow in my lower branch? So current flow in the lower branch is going to be here my net battery divided by net resistance. So it's E by 2R. So I hope you understand the point here. The current through the inductor branch is only here 0. It is today, enough, beta. Just 1 minute. Right, beta? So how to deal with the initial circuit? Initial circuit. For the initial circuit, remember one important point. Inductor don't allow the jump of current. Inductor do not allow the jump of current. But don't misinterpret the meaning of this statement. In my lower circuit, there is no inductor. So in my lower circuit, your current can jump. So initial value of the current in the lower circuit is 0. But after the switch close, immediately current will jump, E by R. But in my upper circuit, immediately jump is not allowed. Okay? So next is, after long time, what happens? After a very, very, very long times. So after a timing when time tends to infinity, after a very long time, how the inductor behave? So after a very long time, it's going to be a steady state. Okay, in a steady state, it is going to reach here the maximum current. Current try to reach here the maximum full growth. So when current is going to be maximums, so it is simply current not changing. So inductor is simply behave as a plain wires. So no, it's a simply behave as a plain wires. So at infinity, inductor is just like a plain wires. Now inductor is going to be plain wire, so I can consider these two branches a mix of parallel combinations. Okay, these two are making a parallel combination. This makes a series combinations. So how much is my R effective? R effective will be two resistance are makes a parallel combination. One makes a series combination here. 3R by 2. So how much is the current coming through the battery? It's R by effective. R by effective, and this will be here 2E by 3R. And this is further is going to be divided into two parts. Equal resistance, so half it will be divided. So I can say my inductor steady state current. So what is the steady state current of the inductor here? It's I by 2. And E by 3R is the steady state current. Right? So my inductor is going to behave as a plain wires. The third thing here is a time constant. If you want to find out the current at any time, you need here time constant first. How to find out the time constants? Time constant here is R equivalent. And this is the equivalent resistance field by the inductor. The equivalent resistance here field by the inductors, not by the battery. So battery has no role, so you can remove the battery. Right? So you remove here the battery, you remove here inductor also basically. Inductor is also not required. So find out the effective resistance across the end of inductors. Just like our capacitors. So it is a R equivalent between the AB points. So we have R, two resistance are makes a parallel combination. These two resistance makes a parallel combinations, and the third one makes a series combinations, right? Okay. So R and parallel here is a two parallel resistance, one series resistance. So it's a 3R by 2. So tau is L by R equivalence. So it's 2L by 3R. Okay. So next one is that growth is exponentials. Growth exponential here means the circuit approach your steady state exponentially always. So it is always try to approach here exponentially. There is no other functions. So current through the inductor, if I'm going to be plot, I don't guarantee about the other circuit, but through the inductors, it is always going to be approached exponentially. So in the beginning, it was 0 to the inductors. And finally, current through the inductor is E by 3R. That was the current through the inductors, right? So just like our RC circuit, this gap is always exponential ratio. Initial gap, final gap. They're always going to be in my exponential ratio. If I consider my current is I, so this gap I can say here is from the steady state gap. So gap from the steady state is my steady state current minus instant current. Initial gap. So this instant gap and the initial gap, it is always in your exponential factors. So what is my instant gap? Instant gap here is E by 3R minus I. And the initial gap is E by 3R minus 0. Right? If we simplify, I'm getting the value of current E by 3R 1 minus exponential. So that is my inductor current exponential. Okay, tau value we have found out. What is the value of tau? Tau value is L by R. Okay, R equivalent was 3R by 2, right? So it is going to be here 3RT by 2L is my tau. So I got the current through the inductor at any time instance, and this current through the inductor any time instant is rising exponentially. Right, beta? Okay. So I hope you understand here how to deal with the LR circuit. So LR circuit are almost similar to your RC circuit, but my LC circuit is quite different. If we have a capacitor with the inductor, its role is quite different. LR circuit is similar to RC circuit, but if you have a capacitor, it is going to be quite different behavior is theirs. So LC circuit we can discuss in next class, but in today's class, try to understand here the LR circuit, okay, and try to relate the LR circuit with the RC circuit. A lot of similarity is there in the LR circuit and the RC circuit. So I hope you remember the RC circuit and you can relate this LR circuit with the RC circuit. Quite similar to our RC circuit.